Well, first of all, I'm John, so I don't know if y'all know me, but I'm a professor here, and I get to introduce Professor Karina Yager today. Hello, Steve. And it's my pleasure to introduce Karina, who came to us from NASA, actually, where she spent a lot of time, and about 9 years after postdoc, is that right? Down at NASA Goddard, and before that, she got her PhD at Yale. Karina's area of interest and expertise is climate responses, land use change as a result of such, and she's been focusing on areas in South America, particularly the Andes, northern Chile, Bolivia, and really cool places to go to. She uses remote sensing techniques as well as in situ observations. You got to have boots on the ground, particularly in those areas that she heads to and investigates. She's been funded by NASA as well as the National Geographic and the Chilean National Science Foundation, which is pretty neat. So she obviously has a lot of international collaborations, particularly in South America, which is very useful when you head to these kinds of places to conduct your research. And today she's going to be talking about some of your land use change studies down in, I think, the northern Chilean region, is that for Bolivia?
I'm covering a lot. So yeah, I'm covering all three regions a little bit.
Fantastic. So,
yeah. Okay, thank you. Thank you for that introduction, John, and thank you so much for coming today and sharing with me and understanding the social and ecological impacts of climate change in the Andes. That's such a big title. I was thinking of narrowing it down at one point, but I'm going to give you sort of the whole broad holistic picture of all the different aspects of changes that we've been monitoring in the high Andes of South America. So just to give you a quick research overview of the types of things that I study what are mountain socio-ecological systems. So I don't see them as so separate ecology and natural systems. So it's social and natural systems are coupled data sets that we study. This is in combination, it's driven by land cover land use change research. So using satellite imagery to understand changes and to visualize processes and to document changes and shifts in land cover. But we really go on the ground to really understand what's causing those drivers and also to verify the ground truth of data that we're processing and understand why we're seeing what we're seeing. So this is a picture of my tent up at the glacier core field to give you an example of sort of what my laboratory looks like out in the Andes. We use a multi-method approach. So in addition to remote sensing for the land cover land use change, we do a lot of vegetation studies. I do a lot on alpine vegetation and on peatland systems, which is a part of the mountain socio-ecological systems that I'll be talking about today. And we also do work with local communities. So it's really important to involve local stakeholders in your research on climate change, because obviously this is they're feeling the impacts of it most. And they're the ones that also have to develop adaptation and mitigation strategies. And a lot of times they don't have available scientific information to them. So our goal is to share in the understanding of the impacts of climate change and also learn from them some of the processes that they're witnessing that we may not have been aware of. I call it that's in the way, but I call this a transdisciplinary approach to climate change, because not only does it just stop with the science, but it's also looking for actionable adaptation strategies. So we take it to the next level in terms of workshopping that and thinking about scenario development, modeling out changes that are happening, and seeing how local people can help increase their resilience to climate change. So I'll bring you to the tropical Andes. The Andes extend all the way from northern South America down through the south. The southern sector is Patagonia. I don't work in Patagonia. You can divide the Andes into a northern and sort of southern regions, but I work more in the central Andes. So this is in the countries of southern Peru, Bolivia, northern Chile, and northern Argentina. This is just a graph, temperature and precipitation graphs that are showing you the gradient of precipitation. You can see that in the northern part of the central Andes, there's a higher gradient from about 1,000 millimeters per year. And it really drops down to, in the northern Atacama, for example, to only 150 millimeters per year of annual precipitation. So there's a big difference in these systems. I use the conceptual framework right now because we're focusing a lot on freshwater resources. So we're using this conceptual framework called Andean water towers. And what are Andean water towers? It's recognizing that a lot of mountain populations around the world depend on fresh water that comes from mountain water. I mean, this is just a graph showing we're the water planet, right? But 97% of that is the ocean. Just a reminder that 3% is fresh water and 70% of that is locked up in ice sheets and glaciers. So really, we only have a relatively little surface water available to us, less than 1%, and the rest is underground and aquifers. So the Andean water towers are especially important for not only rural populations, but also urban populations. This is an example of the city of La Paz. So that's the capital of Bolivia. And there's about 2 million people that live in La Paz. And about 30% of their water resources comes directly from glacial runoff. So they're really dependent on these Andean water towers and Andean watersheds to provide freshwater resources. This is typical for a lot of arid and semi-arid tropical regions where more than 80% of freshwater supplies comes from mountain regions. It supports populations of 1.9 billion people in mountain watersheds. And then if you include all of those 1.6 billion that are downstream, that are depending on the rivers that flow down from mountain areas. They use this water for drinking water, for hydropower, irrigation. They even act as headwaters for major river systems, including the Amazon. So some of the glaciers that we study in the Cordillera del Conote in Peru are headwaters of the Amazon River. So the socio-ecological components of these mountain watersheds, Andean towers, include glaciers, surface and groundwater, peatland systems, precipitation, and irrigation practices. Here's just a conceptual figure to give you an idea of sort of where the aspects that I'm going to be talking about today. We take Andean climate change, including radiative forcing, change in surface temperature warming, increasing emissions, and how that's impacting Andean water towers. And the Andean water towers, we're looking at glaciers, glacier melt in particular, precipitation changes, shifts, changes in natural springs and aquifer systems. And those are directly tied to what's called peatland systems. Now, you may have heard of peatland systems like in the Northern Hemisphere, for example, but there's also peatland systems in the Andes. And they're really dependent on a variety of these water sources too. And the peatlands are important not only for just carbon storage, right? Because they're storing carbon accumulation over millennia. And when they dry out, then they become a carbon source, right? But they're also really important for the traditional mountain communities that live up in the Andes. And they're the primary pastures for the herding of alpacas and llamas, which is just an ancient traditional mountain practice in the Andes. So all the traditional weavings and meat production comes from llamas and alpacas. And they've been practicing this. The domestication of the llama and alpaca was some 6,000 years BC. So they've been practicing this for thousands of years, but they wouldn't be able to actually have llamas and alpacas without peatland systems because it's the primary vegetation system in alpine environments. And when we think about some of the outcomes of these changes in these system components, we can get anything from urban water shortages and increase in conflicts. When there's extended drought periods, a lot of people have to line up for water. The water gets sanctioned, water gets turned off for certain hours of the day. In the capital city of La Paz, for example, the rural downstream water supplies are diminished, which impacts agricultural sectors that are using water to irrigate like large-scale crops like corn and potatoes, for example. We get a loss of biodiversity as peatlands begin to degrade. because there's a drying of these systems, so they're no longer these watershed sort of hotspots of biodiversity, and we get ecosystem service losses. Tourism decline also in relation to glacier melt, because a lot of the glaciers are prime areas for climbing. And so a lot of the local communities also depend on local tourism for people to come in and, you know, host their expeditions, climbing expeditions, that as it begins to melt, that impacts their livelihood as well. Especially with COVID, for example, when no travel was happening at all to South America. What happens when the pastures begin to degrade is that the local livelihoods are no longer sustainable. So there's a lot of outmigration to big urban centers where they're looking for sort of short-term work as taxi drivers or working in small shops. And there's a loss of that, not only of the population in high altitude environments, but a loss of this environmental stewardship. So a loss of some of the general practices that they use to sustain these ecosystems, which I'll be talking about. So for Andean glaciers, tropical glaciers, 99% of them are located in the Andes. The majority, 70% of that, is located in Peru. The second most frequented area is in Bolivia. And then they're distributed between Ecuador, Colombia, Venezuela, has a very small amount, northern Chile and Argentina. The altitudinal range also varies from about 4,000 meters above sea level up to over 6,600 meters. They're subject to high levels of energy forcing due to their location in low latitudes and higher altitudes. The period of max precipitation coincides with the summer period, which is the rainy season, which is about December through March. And then during the dry season, will commence around May through September. But while it's accumulating snow during the wet season, it's also melting in the lower elevations because of the temperature increases that we're seeing. Another positive feedback that's happening in terms of melting causing increased melting is that we get exposed bedrock. So obviously that changes the albedo in relation to these systems, and the melting on the edges increases. Another process is Amazon burning. So Amazon burning is also creating black carbon and soot that gets deposited on the glaciers that also increases their melt rates. So when we're looking at glacier changes, we're looking at the mass balance between ablation, which is the loss of glacier and retreat, and the accumulation. And glaciers are sort of live beings. They're continually changing. They're continually changing on a seasonal and interannual basis. So we have to use a lot of imagery to understand not only the annual changes, but the seasonal changes as well too. And one of the focuses of our research is to look at this equilibrium line of altitude. So that's the line that the melting is occurring the most rapidly and where there isn't really accumulation past that point. So we find that that equilibrium line is becoming higher and higher in altitude because of the surface temperature warming that's occurring and the rates of loss. So we first hypothesized, of course, that the amount of glacier runoff is going to increase with the amount of melt, which would cause like an increase in water availability, right? But we found that also we have passed a lot of our peak runoff from discharge from glaciers. And so that was only a temporary increase. And a lot of them have already passed this threshold. So that we get diminishing rates of return basically on glacial discharge. It's really important not only for the wet season, obviously, that they have this accumulation, but what's most important is in the dry season, there's like zero precipitation in the Andes, especially in areas like the Atacama. So the water systems that are really dependent on glacier discharge, when the glaciers are decreasing in their discharge and there's no precipitation, those areas are most vulnerable to desiccation. So we've looked at, we've done some glacier change analysis, obviously, with looking at trends over time and looking at 19 degrees north to 18 degrees south, a combination of Landsat data and SRTM, DEMs, focusing on mostly Peru and Bolivia, where the majority of tropical Andean glaciers are. One of the techniques that we use is the NDSI, which is the normalized different snow index. Maybe if some of you have heard of like the normalized difference vegetation index, it's very similar. It uses the ratio of the visible and the shortwave infrared to look at reflectives, and it's helpful in distinguishing different types of ice and snow cover. You can apply different thresholds, and you need to do that because there's a lot of also shadowing that occurs in these high altitude environments, which is why you need these DEMs to correct for some of that. And what we found in our analysis of tropical glaciers, that all glaciers in all countries are receding in the tropical Andes, and that the total area has decreased from 2,520 square kilometers to 1,830 square kilometers. This is equal to about a 27% loss in 20 years. So that's 1/3 glacier cover area loss. And there's a strong association with elevation. As I mentioned, that ELA line keeps going up higher and higher. So the lower the elevation of glacier, the more vulnerable it is to greater loss, right? Quicker loss. This corresponds with other studies that are going on in the Andes, and what is also being found is that this glacier loss is not only occurring, but it's accelerating. So in comparison, in an area in a study of 21 glaciers in the Cordillera Real, which is in Bolivia, just a focus on that from 1963 to 2006, 48% of surface area was lost. So that's higher than the average that we found for the entire region. Oh, sorry, did you have a question?
Yeah. Do you have any idea how the glacier loss in the Andes compares to other mountain ranges, like the North American mountains or plateau, those regions?
I haven't compared with those regions exactly, but that's a good question. Yeah. The tropics, like I said, is really vulnerable just because of the low latitudes that it's in the high elevations. So my assumption is that it's higher than the loss that's occurring in northern latitudes, but I'm not sure in the case for the Himalayas. Thanks for asking that, though. I'll see if I can do some more comparison studies of that. That would be fascinating. So the change in length and surface area of 10 tropical glaciers, you just see that this accelerating loss is occurring. In one of the study regions that we looked at, Tuniconderiri, this is an important area for La Paz, for the capital of Bolivia, as I mentioned, where there's a reservoir underneath that provides the drinking water, potable water for the urban population. And what we've noticed is that obviously these are accelerating in their loss. They have been reduced by more than 1/3 in their area. And what we identify as sort of critical, moving from water stress to water crisis projections of water availability for these cities. And as I mentioned, I assume, what we know is that we have projections of global surface temperature warming, and we know that we're trying to avoid this 2-degree increase or 1.5 to 2 degrees Celsius increase. But we know that those areas that are most vulnerable are those in the high latitudes, so the Arctic, for example, and also at higher elevation. So this is just some studies that are showing you that there are more vulnerable higher elevation sites are more vulnerable to air surface temperature increases, according to the models. And we've looked at some of the precipitation records. One of the really huge caveats is that we have a big data gap in meteorological records at high altitudes. It's just because there's no instrumentation at high altitudes. It just hasn't been done. So we've had to actually install a lot of our own equipment to look at precipitation changes but we noticed that there's a warming trend of about 0.15 to 0.2 degrees Celsius per decade above 4,000 meters during the last 4 decades. So that's above the global average. So the major processes and drivers of glacial loss contributing to this 1/3 of total mass loss over the past 2 decades are accelerated increased temperatures at high altitudes, the rise in that elevation of freezing isotherm. There's also shifts, outcomes being that the shifts in hydrological regimes in terms of the amount of runoff from glaciers. There's shifts in precipitation events, which I will also talk about shortly. And an increase in the demand and outtake of water. So just meeting urban demands and also mining. Mining is a big challenge in the Andes because mining is really water extractive intensive. And they have been extracting water from a lot of the underground aquifers as well, but also the surface area water system. And we notice an increased climate variability and extremes. We're trying to dissect some of the impacts of ENSO and La Nina. Yeah.
You mentioned before that like it's past the peak runoff.
Yeah.
So where does that water go then? If it's, I'm assuming you're saying that like glacier melt will occur, but you aren't getting that water.
Yeah, so it doesn't make it all the way down. It doesn't make the connectivities. So when you're past the peak runoff where it can connect to major river systems. So what you'll get is just a trickle loss of water, but it'll stay in situ. Does that make sense? And so what happens too is that you want the runoff to be more than well, what's happening is the runoff is more than the accumulation that's happening every year too. So instead of greater accumulation during the wet season, you have a decrease in that as well. So the outcomes of glacier loss. This is a great profile of one of the glaciers that I've worked at in Peru, and then sort of looking at the melting right at the edge of the glacier. But a lot of these glaciers also for local communities, they're recognized as apus, which means a deity. They're actually honored and they're given offerings because they're seen as providers and protectors of their livelihoods. And so there's a lot of cosmological impacts too for the impacts on traditional communities. But also there's increase in conflicts over water access and water use. And this is between rural and urban communities where contracts are set up with incoming hydro reservoir companies where they want 60% of the water and they'll allocate maybe 30% of the water to local communities. Well, there's obviously some conflict in that, whether they need more or less. There's a lot of hydropower in the Andes dependent on glacier water runoff. And so there's concerns about that for the future. There's also hazards associated with glacier loss. So increase in landslides and avalanches, and also glacial lake outburst floods you may have heard about. They're called GLOFs, where the increased melt is accumulates into a lake, and it's sort of held in place by glacial till. But there's a point where so much melting can occur during a season, or that combined with extreme precipitation event, and there will be outburst floods that will go down and wash out communities or wash out agricultural fields down below. And increased hazards for climbing, with obviously increase in crevasses, and tourism declines, agro-pastoral production declines, and also loss of climate data records. So this, for example, is SoMAS glacier that's in Bolivia. It's the highest glacier in Bolivia, and it has an ice core history of 25,000 years. But the loss is the melting is not only occurring on the sides, but it's occurring also on top. So that's corrupting the data that you can extract from some of these ice cores. This is a picture of Chacotaya, which was actually the highest ski resort in the world. This is also in Bolivia, and it shut down in the 80s, in the late 1980s, because of how much glacier loss there was. They don't have those snow making machines like we have out in Colorado. But did some modeling to predict when it would disappear, and this was taken in 2009, this picture where schools had gone up to sort of witness the disappearance of the glaciers. This is an example of sort of these festivals and these pilgrimages that usually hundreds, thousands of tents actually that go up to the glaciers. They make pilgrimages up there to pay homage to the glaciers. Traditionally, they would actually take a piece of the glacier and bring it back to their community and like make it as an offering in their pastures and their agricultural fields. But then they noticed that obviously the glaciers were melting so quickly that they put in regulations at a social level that you can no longer take pieces of the glacier. And they will stand with water bottles underneath the glacier, filling that up with basically what's like holy water. Another aspect that we look at in relation to alpine ecosystems is vegetation. So as these glaciers retreat, obviously there's new soils exposed and vegetation expanse is occurring in high altitude regions. But we want to know what types of species are coming in, whether they're the traditional endemic alpine species or if they're lower altitude invasive grasses. So we set up what's called a glorious site that says Global Observation Research Initiative in Alpine Environments that originated in the Alps in Austria in the 90s. And we set up the first glorious site in South America in 2002. And what you do is you select a target region of high altitude and you pick 4 different summits at different elevational tiers and inventory all of the vegetation that's growing on these mountains. And we install soil temperature loggers and meteorological stations to look at changes in climate parameters that are also impacting vegetation change. So this is an example of sort of where we set up these monitoring sites in relation to glacier retreat. This is in Peru. And this is a picture of some of the glorious sites themselves and some of the species that are growing, the alpine species that are growing at high altitudes. Alpine species are unique because they're very slow growing. They have deep, thick root systems to access water deep underground, but also to increase their resilience against cold temperatures, right? But the question is how many invasive species of grasses are coming in? But we found this is an example of a glorious site right next to less than 5 meters from the glacier forefront. So we're getting the first sort of glimpse of what ecological succession looks like in these deglaciated forefields. And we found new species. We have found new species up at high altitudes. And we've seen, these are just an example of some of the species that are growing up there. I don't have to go through all of the cover at these different sites, but just to give you an amount, 141 different species in alpine, in this alpine region. And we can link this, this can be linked with other, we do, we compare these vegetation assemblages with other alpine regions across the world. So we look at those occurring in the Alps and those occurring in the Rockies and in the Himalayas, actually. They just installed some glorious sites there. Along with vegetation advance, we've actually found the highest amphibians in the world that are also moving up to higher elevations. So as we know, with the change in climate, there's a shift in biomes, right? The shift in biomes to northern latitudes and also to higher elevations. Well, that's exactly what we're seeing on the ground in the Andes with the movement of amphibian species. But we've also found that with this increase in new amphibian populations, what we didn't expect is that a Kittredge fungus, which is the #1 killer of amphibians now globally, it's a fungus that messes with the electrolytes of the amphibians so that they can't breathe anymore. They essentially have a heart attack. But we thought that this area would be free of the Kittredge fungus, and unfortunately it's not. That's also moving to higher elevations. And we also found in the study that the deglaciation trend is increasing. So we looked at a particular corridor where we have our Gloria sites and our amphibian monitoring sites, and looking at the amount of loss within this corridor, because what happens is this provides an example for species movement over in between regions, right? But that trend is increasing, and from 1980 to 2005, it was about 9.5 meters per year of loss in that corridor. That's nearly doubled to 18.4 in between 2005 and 2015. So again, that accelerating loss of glaciers occurring. One interesting thing that we did find, though, is when we're resurveying some of these sites, we go back to those Gloria sites every 5 years and do a new inventory of plant species, and also check on other ecosystems that are up there, such as amphibians. We found that some of the amphibians were able to make a recovery after the Kittredge fungus. So that also implicates that some, as long as there are watershed components that are available to amphibians, they have a chance for adaptation. And one of those watershed components are those peatland systems and small waterways that I will be talking about. We also look at exposed soils from deglaciation, and just to let you know that we've done some freeze thaw analysis of rotifers and alga in relation to this. And after 6 years frozen, microbial communities in the mat were sequenced and revived to test their adaptation to extreme freeze conditions. They've been actually able to come out of dormancy. So this is sort of like those moss zombie stories that you hear of new bacteria coming back after deglaciation retreat. So the overall consequences for alpine biodiversity, that, you know, those adaptive traits that were once helpful, such as growing those long, deep root systems, are no longer adaptive in these new changing environments. Instead, short grasses are having an advantage. We see a complete upward migration in biomes visible. We have the evidence of invasive and competing species, including the pathogens moving to higher altitudes. We're seeing entirely new vegetation assemblages, or the possibility of no vegetation growth in some regions. And we have an increase in erosion. That's also with the bluffs and with the avalanche slides that are occurring, and the amount of rapid runoff that would occur. So there's just very poor soil development in mountain environments in general, and it can be easily washed away with extreme events. So as glaciers continue to retreat and experience this accelerating loss, another system that's really becomes more important are these peatland systems. Now, peatland systems exist also throughout the Andes, and they're just downstream, and they're basically, what they're doing is they're catching the water runoff from glaciers, right? And they're regulating that water. So they're slowing down the runoff. They're also catching precipitation, and they're also, because it's peat, what peat is that it grows so fast that it doesn't completely decompose before the new growing season. So all of the carbon that it's uptaking in a given year gets sequestered. That's the definition of a peatland system. A fast growing vegetation system. And, you know, peatlands exist in all biomes, and they cover an estimated 3% of the Earth's total surface, but they store 30% of the soil carbon, so they're really important for carbon sequestration. And these are an example of the peatland systems in the Andes. 80% of them are located in the northern hemisphere, and the rest are in the tropical regions. There have been treaties, international treaties, to help sign and protect some of these wetland systems, but not all of them are protected. The largest one is in Bolivia, actually, and they are, you know, hotspots of biodiversity, important for capture and storage and regulation of water. They support the livestock production, as I mentioned, and they influence the regional carbon cycle. They also sequester 10 times more amount than those in the northern hemisphere, and that's because they're growing all year round, as they're located in the tropical regions. They're smaller in their total area, but they sequester more carbon. So our job is to understand the articulation of peatlands with these Andean watershed components. We are interested in their total area and the condition of these systems. So here's a figure just showing you a healthy bifidal peatland system here with animals grazing on it and lots of water present. This is an example of a degrading system where the peatland cushion bogs are beginning to desiccate, and what's happening is the invasive species, not really invasive in this case because they're endemic to the area, but they're grasses, so they're not as important in carbon storage at all, and also less helpful for pastoralism. They have less nutritionist value. And then here's a system that's been completely desiccated and has died off. So peatlands differ in sort of in the lens that you use, like, so if you're saying, well, what is their primary water source, or also what are the social components of these peatland systems? So we found that traditional communities have been managing these peatland systems over long periods of time through irrigation. So they actually manage the glacial outflow of water, divert it, and use it to sustain these peatland systems and expand these systems. But what happens if there's outmigration from mountain areas, then we lose that local sort of environmental stewardship of these systems, and they become more vulnerable to desiccation. So I've already mentioned they act as seasonal buffers in hydrological change and managing that runoff. This is a good example of their relationship to the glacial watersheds. They're threatened by shifts in hydrological regimes. So when precipitation events are occurring and the duration and intensity of those precipitation events annually, we've also noticed a drop in the water table and extended drought periods that threaten the resilience of these systems. So we want to understand, I'm just moving a little bit quicker because I see that we're already a little bit closer to towards the end, but I'm not done with all my slides. So I want to understand what the resilience of these systems are. So when there's a large drought event or something like that, are they able to recover? So we use our multi-method approach. As I mentioned, we do a lot of the remote sensing of the peatland systems and use in-field spectrometer to measure their reflectance and couple that with what we're seeing to make a spectral library of different types of conditions of peatland systems and their conditions, and also their environment, their vegetation composition. We install, we do a lot of coring, so we look at the depth, the total depth of these systems, so we can estimate how much carbon storage actually exists in these systems. We look at carbon content. Are some species of peatland systems storing more carbon than others? We install also stream level loggers, and we do isotopic chemistry of the waterways to see what are the main sources of water to certain bifidal systems. So we say where are they getting their water, and then also how are bifidal systems in turn contributing to downstream waterways. So we have to install our own meteorological systems in a lot of ways. We do the stream flow to understand the waters that's coming in and out of these systems, and vegetation composition. This is just an example of us doing a vegetation survey, and we look at species composition and diversity, net primary production. So we also do biomass estimates for forage value. When we are coring, we want to know how deep, how old, how stable, how have they changed over time, and what's their total carbon storage. Some of these systems are over 10 meters in depth, and this is comparable to 7,000 years of age. So they've been developing throughout the Holocene. But what we found is that, and that's sort of some of the fastest growing peatlands in the world, with 2 centimeters per year. But we also find that they're desiccating so quickly in recent years. So peatland systems that have been accumulating for thousands of years are all of a sudden rapidly drying out in a matter of 5 to 10 years with increased global temperatures. So that has an impact on, there's different regional decays, stages of decay, but that's impacting the total soil storage carbon. We find that waterlogged conditions is the most important variable. Water has to be present in these systems for as much time as possible on an interannual basis for them to survive. So when water is not present, that's when they begin to dry out. But what we've seen is that there's a drop also in not only from the glacier runoff, but also a drop in the water table. So what happens is that the species, the peatland species that are growing on top, they can't actually reach the underground water table anymore, and they begin to dry out. We've calculated the carbon stocks for 2 different areas, and in the high Andes, and we've obviously they become from a carbon sink to carbon release, and not only CO2 but also methane is stored in these systems. We worked with local communities to, like I said, do outreach on the science that we're finding, but also to learn from them the types of challenges that they have in managing these changes in our mountain ecosystems. Here's sort of a diagram showing sort of these visual resources that we like to produce for them in terms of understanding peatlands and their relationship to runoff and precipitation and glacier melt and the underground water table. Here's a good example of where high erosion is happening from this glacier SoMAS that's undercutting this peatland system. So the water is now running, instead of over the system, it's running deep under the system, and one side of the peatland system can no longer access water, so it's desiccating and drying out versus the other. Local communities are managing bofidales in different ways. They will burn the edges and inundate it with water for several years, but there's a lot of conflict in, who's burning what pastures, and bringing in tractors to divert water, but that cuts off from communal water management sharing. There's an increase of privatization of these peatland systems, so they're not coordinating water connectivities across the watershed. There's a lot of cleaning of canals to make sure that water flow is occurring. And there's also some rebellious acts against mining companies where they will be burning a lot of systems just to show that they own these systems in response to water extraction that's occurring in the region. This is an example of the northern Chilean region in the Atacama Desert. So this is an old peatland system that has been completely desiccated because of water extraction from mining. Mining is important in Chile for copper and nickel and lithium. And we've documented the amount of pastoral communities that were once in this region, and then the depletion of, and as they lose their primary water sources, they can no longer live in high mountain environments at all. Now, the mining companies have some sort of concessions that they have to meet with the local communities in terms of returning water, but they don't return water at the right time periods or in the right places. So there's a lot of conflict there between the companies. So mapping of peatland systems, we were trying to map, just like we mapped the glaciers, we're trying to map all the peatland cover and looking at over 100 sentinel images to analyze every 5 days to map humid meadows in general. So wetland systems at high altitudes, including the peatland systems. We're not able to ground truth all of these sites, obviously, so we use a lot of the literature from the National Herbarium and from peer-reviewed articles that document peatland presence in the bofidales, so that we're able to come up with classes of peatland categories and do mapping, although we've done case studies in particular areas where we're able to really resurvey the vegetation and see if it's matching up with the remote sensing image analysis that we've done. So for example, this is in SoMAS. We set up 110 different quadrats and different bofidal classes to register the families, much like we do with the alpine vegetation survey, including documenting species composition and cover. and relationship and amount of soil carbon. We've seen a decrease in the total area of healthy bofidales, and as I've shown in those pictures, what's happening is they desiccate, and then the dry grasslands are moving in. But you can see in some communities where, for example, this is in Caribe, which is one of the communities in the national park, they're actually increasing their peatland cover by applying irrigation methods. So we know that that's an effective measurement for adaptation in these regions. We've also looked at the NDVI response to climate variables of precipitation and temperature. So what we want to know is how, after looking at the different dependencies of peatland systems on either glacier runoff or precipitation as their main source of water, how long before they green up after a big precipitation event or onset of the precipitation season. So we look at that correlation, and we find that there is it happens differentially in different regions, where there's a lag time between the onset of precipitation between 1 and 2 months with the onset of the rainy season to when you have the green up of the peatland system. The northern systems are slower in the green up, but that's because they have a lot more glacier runoff still available to them than the southern regions, which are quite dry and have very little precipitation overall, but are completely dependent on it in some cases as the glaciers have retreated. So we noticed that, these alpine peatland systems cover a much larger area than the glaciers. So they're going to be playing a new major role in maintaining watersheds in mountain regions. So they need to be highly conserved and prioritized in the cases of water regulations and water sustainability in high mountain environments. So we've calculated for different areas of Argentina, Bolivia, Chile, and Peru, and for different hydro basin watersheds. We've also done household surveys with the local community members. And for example, in Sahama National Park, we did 83 of the 179 households that live in Sahama. That's about a 46% sample size. I'm not going to go through all the questions. We have over, nearly 100 questions that we asked them about what are their perceptions of climate change, what are their perceptions of bofidal change, what do they think are the drivers of bofidal change, what are their memories of past climate events, what are the connections between their local production, how much do they depend on pastoral production versus outside economic opportunities, and what are their primary sources of water. The answers that come in for a question of, so for example, what's a main driver of precipitation change? Well, it's really in line with some of the things that we're finding as well, a decrease in precipitation, but they also poor management of water. So that's recognizing the increase of privatization and less communal management efforts to distribute water. Hardened soils, greater evaporation due to heat increase. I mean, I think I'm surprised, and I'm also happy that they're learning about these global change processes and also the impacts that they're having on their local ecosystems. Drying of springs, rapid deglaciation, and climate change in general. So challenges to water access, there's a scarcity, there's the reduction of the water springs. These are just answers that they gave us. So river water level is dropping, reduction of precipitation, all the things that we're recording in the science are also being witnessed at the local level, so to speak. So we define that the bofidales are decreasing. The bofidales is the local term for peatland systems, are degraded because of the combined social and ecological impacts. Climate change and extreme events are having negative impacts on the primary water sources and the water table. And the reduction in irrigation is needed to be given attention to. Adaptation strategies can include, more technological investments to manage water distribution and access to water resources, increase their productivity by increasing irrigation, by increasing communal management. I'm going to skip through that real quick. So another thing that we've done is to model out the precipitation rates. Using the NASA Center for Climate Simulation at Goddard to look at to characterize the spatial distribution, the precipitation rates and diurnal cycle of precipitation for the Central Andes. So trying to figure out where it's raining, how much it's raining, and if that's changing at all according to the RCP. So the representative concentration pathways, which you know from the latest IPCC reports that this is the projections of change in radiative forcing and change in the energy balance, and how there are, you know, 4 possible pathways that, you know, are being very conservative of 2.6 increase watts per meter squared versus 8.5 if we're not going to do anything about it, right? So our model looked at the Altiplano regions and including Sahama National Park, and the outcome was, and we ran it at different RCPs, which you can't see up there. Sorry. I don't know how to turn that off, but at 4 and at 6 and at 8.5, and what we see is that the precipitation differences are definitely significant in all but the 2031 wet season. So these changes aren't going to happen right away, but they are going to increase after mid-century. Yeah, thanks, Sean. I don't know if I can get this. And there's a general overall decrease in precipitation amounts up to 300 millimeters for most of the regions of the Altiplano. Now that may not be a huge impact on the northern regions. Well, it's still an impact, 300 millimeters per year in an area that only gets 1,000 millimeters per year, right? But in those areas, especially in the Atacama Desert and in Sahama National Park, where the annual precipitation is 300 millimeters per year anyway, that is a huge reduction in absolute total precipitation. And the average precipitation rates are actually predicted to increase. So what does that mean? That means that there's greater downpour events. So they can get the same amount of annual precipitation, but what will happen is it will come down in fewer days. And that can lead to extreme events.
Sorry, I'm just trying
Yeah.
to get rid of
Oh,
this.
thank you.
There's a
Hide video
Yay.
panel right in the middle.
Yeah. Thank you.
Okay, thank you, John. Yeah, so you say we were at 16 RTP, that's a corner.
Oh, crap.
That's okay.
And then hide screen controls is to hide the bar. too.
Yeah, you go.
Yeah, but I exited
Now
here.
go back, right there.
Sorry.
That's okay, this is great.
Really good.
Yeah, that's great.
That's the-
Okay. So just the results thus far suggest that precipitation in the Central Andes is expected to decrease by 11 to 18%, up to 500 millimeters per year in some areas by 2087. 15 to 25 fewer days with precipitation and an increase in precipitation rates at 0.5 millimeters per hour on average. And so despite these changes, the spatial coverage and diurnal cycle emerging at the time of day that the precipitation comes is not changing, right? But the total amount is changing and the intensity is changing. And this is an example of a Bofedal area that's, you can see here, this is a pipeline. This is in the Atacama Desert. And he's basically the last herder in the area because of all the mining extraction that's been occurring in this high mountain area. And this is what we're trying to avoid this complete defecation of high mountain Andean areas. You can see that glaciers are practically absent. So, and also in addition to going forward in time, we're going back in time. We found a historical archive of images of glacier extent in 1931. So this is way before the satellite record. Our satellite record starts in about 1972 for glaciers. But we were able, there was this really awesome brave two geographers, Robert Shippey and George Johnson, who flew a Blanca Peacemaker plane in Washington. They named it 2 planes, the Washington and the Lima, and they did 454 flight hours in 1931. And they flew over all kinds of sites, including Machu Picchu. It was the first aerial photographs of Machu Picchu from the air, but they flew over all of the glaciers as well. So what we've done is we've tried to recreate their flight paths across the Cordillera Vilcanosa region where we're studying some of the glaciers, so that we can push back that satellite record as well to look at really historical changes of glacier melt and look at the trends of loss across time. And see how that's accelerating more in recent years, obviously, but it gives us a new look at glacier extent and, you know, and in a time where before we even had the satellite record. So this is just an example of some of that repeat flight photography and some of the glacier tongue analysis that we do. And looking at some of the, sorry, I went too fast, and looking at some of the corridors that are opening up. And looking at trends with the satellite imagery as well to look at when are there rapid periods of loss. So we found a glacier area at the past increased by 95% between 1931 to 2018. It means almost complete loss of it, and greatest decadal loss of 61% occurring between 1988 and 2008 so far. We create a lot of data visualization products for communities to have access to, because like I said, a lot of them don't have access to the scientific data, and it's really helpful for them in decision making. They say they have no information from the municipal government, for example, telling them they know their glaciers are retreating, but they don't know how much. So we try to create a lot of outreach story maps that are also available in Spanish and English, where you could zoom in on certain areas and look at actually what are the species growing and what is the classification of this Bufetol and what's the vulnerability of this vulnerable Bufetol to desiccation. We worked with local schools too to look at reflections of climate change and, you know, thinking about what do you find in the mountains, you know, how do you feel in the mountains, how do we conserve the mountains. We've done story maps on our field expedition activities, where we're showing like these historic aerial photographs in 1931 and the amount of amazement in their faces when they see, oh my gosh, that's what Ausungate, one of the important apus, looked like, you know, almost 100 years ago when their grandparents were alive. There's a multi-decadal glacial change where we show the glacier change analysis, and there are interactive dashboards that we've created, so you can look at different NDSI measurements. And because we don't have a lot of time, I'm not going to be able to show you all of that, but you can pull up certain glacier outlines and then choose an NDI threshold value or an year and come up with the actual glacial extent for that year and look at trends over time. And this is sort of I think I can say it. Yeah, this is sort of a compilation of coupling that historic imagery through a fly through of that original 1931 Shippey Johnson expedition flight. So that, and these are the types of sort of visually stimulating resources that are available to local communities to engage in the conversation about water management, and especially when mining communities are coming into their backyards and saying, hey, we want to use your water. This is giving them leverage to have not only the visual data, but also the scientific data to say, no, you know what, we need our water because we see that these glaciers are retreating so quickly, and it's having huge ecosystem impacts on our communities. Short clip from one of the fly-throughs. So thank you very much for spending this hour with me and learning about the social and ecological impacts of climate change in the Andes. And I want to okay.
Questions?
You have tissues for all the tears being shed.
Sorry.
Yeah, it's
Yeah.
remarkable.
Yeah. Yeah.
I have a question about when a glacier begins to melt And you're monitoring the perimeter of the glacier and the area of the glacier. How does that correspond? Does it correspond exactly to the runoff from that glacier in terms of prediction of water? Is there basal runoff that's not measured by the perimeter?
Yes, so some of that runoff is just going to seep into the underground water table, right? But what we do also is we set up stream loggers. Loggers down below the glacier, we identify the main outflows of glaciers and measure it that way. Yeah,
And does it correspond closely? Or is there a
Closely to the
correlation you
loss?
see?
yeah, yeah, in some cases, more likely we're looking at trends, so we're looking at, is it an increase in the dry season or increase in the wet season and why? So it's difficult also to do volume measurements, so you have to use a high resolution DEM, and in some cases LiDAR can help with getting that volume measurement of the glacier to see how much water is actually being lost. Yeah.
I have actually a question related to these fading glaciers. First of all, even like RCP 2.8.
Yeah.
2.6,
2.6.
will they be there by the end of the century? or-
By the end of the century. I would want to say, I would say no. I would say even RCP2, because we're talking about these are higher latitudes. We're talking about that's the global average, right? And we already know that at the high altitudes, they're above and beyond that. And by measurements of our trend, we're up to 0.33 per decade. So we're already exceeding that 2 degrees. And then once they reach that warming threshold, there'll be a continual loss, just like we see in Greenland. Yeah.
And then you were mentioning this, well, kind of counterintuitive phenomenon that we are, well, in many places, in many watersheds, there you are behind the peak flow of these glaciers.
Yes.
So you would expect in warming climate, more
Yeah.
melting, more water
More
coming down.
water coming down.
And so we are now beyond the peak. Is that true for pretty much all those glaciers? Or are there differences between north and south or high elevation? low
Well, that
elevation?
one study that we did in the northern is where, the glaciers are, greater anyway, and they've already passed peak discharge. So we
So
assume
when
that
did that happen? Like 20 years ago or 50 years ago? Or when was the peak discharge then?
2009.
Okay.
No what fraction of the net loss is evaporative? Is it significant? Or
Oh, that's a good question. Yeah. Yeah, I don't know. Yeah. Yeah. But we do know that it's melting, even installing our meteorological stations like on a glacier to go back and move it again because it's just so much melt. Evaporative melt occurring, yeah.
I'm really extremely skeptical about climate model ensemble predictions of future precipitation.
Sure,
trends
sure.
over mountains.
Yeah.
I'm curious how good are the observations of precipitation, say in the last 40 years? Like, do we know if it's increasing or decreasing observationally, the mean precipitation?
That's an issue also with just the amount of data that's available.
Like, you don't have many weather stations, right?
Yeah, there's minimal weather stations at high altitude.
What
Yeah.
are the oldest ones in that area?
Well,
Yeah, more than
oh my
20
gosh,
years.
we have so many data gaps where like they install a meteorological station with the establishment of, for example, like a national park. And then,
Will it be there
but
like 5 years and then?
yeah, 5 years and then nothing. Yeah,
So,
yeah.
is there any reason to think did you call them peatlands?
Yeah, peatlands.
Will they move up? Is there a possibility that the whole ecosystem will move up?
Yes.
That would be not as bad as it's at. It's still bad, but still, the whole system should move up.
We've seen some of that. We've seen what we call opportunistic peatland systems.
Yeah.
That begin to develop right next to glacier melt runoff. But the thing is, they're not going to be able to sustain that long because that glacier is going to retreat faster and it's not going to be having that runoff. So it's going to be a short temporary growth. And then it would become either primarily dependent on the precipitation course. But if it's already developing in relation to glacier runoff, that's probably a really vulnerable system.
Aren't there higher precipitation rates at higher altitudes? I'm grasping for like positive straws here.
I love that. I love that. Yeah, so we will, yeah, so, I mean, it's possible that it'll shift to a regime where the precipitation will be enough.
Yeah.
But what I'm saying is that certain certain peatland systems are dependent on glacier runoff, and some are more dependent on natural springs and precipitation. So I think it would depend on the system itself. Yeah,
So are any of their aquifers, I was thinking about the drinking water
yeah.
sources, I mean. Is rainfall feeding any aquifers where you have water stored or?
Yes, yes, and actually, we've looked at some GRACE data to look at some of the aquifers, and they're all declining. I didn't include that, but yeah, they're all in heading towards stress.
Even though rainfall hasn't measurably decreased.
But we don't.
We don't know. We don't know the details exactly of a decrease, but we know that the local testimonies are saying that precipitation has decreased. We know that there's a shift in the onset of the so we're getting about the same amount of precipitation, at least according to the models and according to what we're seeing. But what's happening is it's coming in events, in
Yeah.
extreme events, in
Yeah.
downpours,
Yeah.
and that has greater implications for water runoff.
Mhm.
So it's not as replenishing of the underground aquifer systems.
Yeah.
Yeah.
So I hear you saying that the peatlands like help to replenish like the groundwater, right?
Yeah.
So I was just wondering, like the you said some peatlands are being destroyed. Like, do you know, like, how much of these are being destroyed or being desiccated? And like, is there any possibility of restoration?
After a certain point, you cannot restore a peatland system. You cannot. It's just impossible. And they've been, like I said, they've grown over, thousands of years. It's just like lost, like cutting down the Amazon, it's can't reinvent it. So the best case scenario is to identify those that are vulnerable to desiccation before they're fully desiccated, and then implement irrigation practices to restore that system. But that's going to mean taking water from more far away sources. So because the local water table is dropping, and because the water runoff in the rivers is also dropping, you have to come in with technology that can transport that water from those distant sources and bring them in to kind of maintain these systems.
Wow, and I was kind of thinking what Levi was saying, I was saying, well, maybe your mean precipitation would actually increase in some areas in the tropics at the higher elevation and stuff, but I guess the question is your new steady state even gonna be somewhere where there aren't glaciers at all?
Yeah, and the other problem is like just with precipitation, because there's that change in that freezing isotherm too, where snow would be more able to replenish these underground aquifer systems. Rain doesn't. Rain just erodes. It just goes right off.
Awesome. Okay. Thank you, Dr. Yager, and very much.
You want to keep talking about this, sir?
Yeah, there's lunch in the
lunch,
Swanson
yeah,
room.
great.
So